So we're going to determine the area between this graph and the x-axis. You can use a definite integral to do this, but we are going to do it, assuming we haven't learned about definite integrals, we're going to do it using the limit of a sum definition. So to do that, we have to remember that the area is going to be the limit as n goes to infinity of the summation I going 1 to n of, and this is a Riemann sum, of f of c sub I, any value in the interval, times delta x, which is the length of all the subintervals. So delta x is always the length of all the subintervals we're using. So it's the length of the whole interval, which is 1 minus 0. You can see the length is 1, but your general formula is b minus a over the number of intervals, which is n. So we have 1 over n for delta x. C sub I is any value within each subinterval. So the easiest choice for C sub I is always the right endpoints. So if you use right endpoints, the formula is very easy. It's a, where we're starting, plus I times that delta x we just calculated. So in our case, a is 0. So C sub I is just I times delta x, or in other words, just 0 plus I times 1 over n, or just simply 1 over n times I. So our formula becomes this for our area. The limit as n goes to infinity of the summation as I goes from 1 to n, so we're really adding up an infinite number of these subintervals, of f of c sub I, which is 1 over n times I, times delta x. So the only thing we have to fill in here is what f of c sub I is. Well, the function f is 2x minus x cubed. That's what we're trying to find the area under. So f of 1 over ni is you're just going to replace those x's with 1 over ni. So we're going to have 2 times 1 over ni minus 1 over ni cubed. And that's all times the delta x, which is 1 over n. So now you just have to calculate this limit using summation formulas. So this is something we've done before. So you just do it like we always do it. Here goes. The n is a constant here as far as the second part goes. It's changing when you take the limit, but I can factor out the 1 over n outside of this summation. Like so, because it's just a constant. It's not a constant for the limit, so I don't want to factor it all the way out. So I'm going to use my summation formulas to figure out the summation of I. So here. The summation of I is n times n plus 1 over 2. The 2 over n was a constant. I is this for some formula. The 1 over n times I cubed would be 1 cubed over n cubed. That's my constant. And then the summation of I cubed, which by formula is n squared times the quantity m plus 1 squared over 4. So this was just the summation of I. This is the summation of I cubed. Now I have to apply the limit. So looking at the limit, you're going to have to distribute the 1 over n. And what that does, if you look at each separate term, is the first term you have an n squared. When you multiply this 1 over n through, you're going to have also an n squared on the bottom. So that means when you take the limit as n goes to infinity, you're just looking at the leading coefficients, because that's what you do when the degrees are the same. The second one, the degree at the top is going to eventually be n squared times n squared, which is n to the fourth. And the degree of the bottom is also going to be n to the fourth. So since we're taking the limit as n goes to infinity and we have the same degrees top and bottom, we're just looking at the leading coefficient. That's what makes this so easy. It looks very complicated, but it's going to be easy. All you have to worry about here is the leading coefficients. So with that, when you take the limit. So with that being said, the leading coefficient of this first term is going to be 2. That's going to be 2n squared. And the bottom is also going to be 2n squared. So that's what's going to result from the first term. From the second term, the top is just going to be 1n to the fourth. The bottom is going to be 4n to the fourth. So 1 over 4. That's the results of the limits. This is easy. 1 minus 1/4 is 3/4, and we are done. That is the area under this graph between 0 and 1. And as you know, it's also then the integral of this from 0 to 1. So that's it.